This is a video intended for my introductory statistics course, but I hope it's useful for and interesting to people around the world. In this video I'm going to be talking about how to simulate a particular baseball player's season, Rod Carew's 1977 MVP season with the Minnesota Twins, on a spreadsheet. If you're looking for something really fancy, this video is not it. This is a video that is intended to help somebody be able to actually do this on their own if they learn it well enough. In 1977, Rod Carew had quite a great year. He had a .388 batting average. He got a hit in 38.8% of his official at-bats. He had 239 hits and 616 at-bats. He had like 14 home runs, 100 runs batted in, 128 runs scored. Really good. And he was my favorite baseball player when I was young, and so I'm really excited about doing this. There are some prerequisites that you should have in understanding what's going to go on in this video. You should be familiar with discrete random variables and their corresponding probability distributions, and in particular you should be familiar with binomial random variables. We're going to model the number of hits per game as a binomial random variable. And you should be familiar with spreadsheets. The simulation itself is going to have some assumptions. We're going to assume a full 162 game season, even though he didn't have that full season, he missed some games. We're also going to assume 4 official at-bats per game. That obviously doesn't happen every game. And by the way, what is an official at-bat? Basically, it's an at-bat where you are not walked and not hit by a pitch. If I recall correctly, I think that covers it, but maybe I'm wrong. They either get a hit or get an out. We're going to assume there are 4 official at-bats per game. Again, he had a .388 batting average. He got a hit in 38.8% of his plate appearances where he had an official at-bat. And that is the probability of success as a binomial random variable. And n equals 4 is the number of trials per game. The variable itself is going to count the number of hits per game, and again we're modeling that as a binomial random variable. Is that really true? Does it really satisfy the binomial assumptions? Not necessarily, but it seems pretty reasonable, and it's certainly the simplest model that you could use. So here we go with the spreadsheet. So I'm calling this game logs for simulated 1977 season, assuming 4 at-bats per game. Again, it's a simulation. It's not going to reproduce his season exactly, okay? It's just a simulated season based on a binomial random variable of number of hits per game, where p, the probability of success, is .388, and n, the number of trials per game, the number of official at-bats, is going to be 4. Right here I can make a table showing you this probability distribution, both as a PDF, a probability density function, giving you the probability that x equals a specific number k, 0 through 4, number of successes, number of hits, and a cumulative distribution function, the probability that x is less than or equal to k. Now there are formulas for these probabilities that are based on combinations and based on something called the binomial theorem, but with a spreadsheet we don't have to get into that. We can use a built-in function called binomdist, whose syntax includes, here we go, the first input being the number of successes that you're thinking about, in this case 0 through 4. The second input after a comma is the number of trials, that would be the n. The third input is the probability of success, that would be the p in cell B1. And the fourth input is cumulative, which would be false for this first column, a probability density function, and true for the next column, column D, that would be a cumulative distribution function. So the first entry there for this one is going to be k equals 0, that is in cell B5. The second entry, number of trials, is in cell B2, and I want that to be a fixed cell reference, so here's where your familiarity with a spreadsheet would be helpful. I can use $ to make that fixed, put another comma. P, the probability of success, is in cell B1, I want that to be fixed, and then I want a false for this first column because it is not cumulative. You can see the answer here is about 0.14. Go ahead and enter it and see 0.14 is the approximate probability. Now I can copy and paste this down. The B5 will get updated to a B6 because I did not use $, but the B2 and B1 will stay the same. The probability of getting 1 hit in 4 at-bats is 0.356 approximately. The probability that he gets 2 hits in 4 at-bats is 0.338. Of getting 3 hits in 4 at-bats is about 0.143. And finally, going for 4 is about a 0.023 probability. To do the cumulative one, it's the same kind of thing, equals binom dist. The only difference is the end. You would use a true instead of false. Oops. Everything else stays the same, but now do true. This first entry is going to be the same because it's the probability of x equaling 0 is the same as the probability that x is less than or equal to 0. But then other numbers are going to be different. You could also get these numbers, for example, the 0.496 by adding the previous cumulative probability and the next individual probability that x equals 1. 0.14 plus 0.35575 is going to give you this, etc. 0.496 plus 0.3383 is going to give you this. These numbers add up to 1. This number is 1. All right? So that's the basic probability functions. Now we want to get into some simulation based on that. Before I do that, let me go ahead and reduce the decimal approximations here to 3 places after the decimal for each of these, because that's going to be the basis of my simulation. What I'd like to do here is for each game, and there are 162 games here, you can go down and see there are 162 of them. For each one of these games, I want to use this built-in function array in between, which will generate random whole numbers, in this case between 1 and 1,000, that are going to help me decide how many hits he gets each game. 251 is what came out first. And how do I decide how many hits he gets per game? Well, basically, I can use these decimals here for the cumulative distribution function to decide what the whole numbers over here represent. If I get a whole number between 1 and 140 inclusive, that's going to represent getting 0 hits in 4 at-bats. On the other hand, if I get a number between 141 and 496 inclusive, that's going to represent getting 1 hit in 4 at-bats. If I get a number between 497 and 834 inclusive, that's going to represent getting 2 hits in 4 at-bats. Between 835 and 977, that will represent getting 3 hits. And between 978 and 1000, that will represent getting 4 hits. Based on this probability distribution, based on multiplying these numbers times 1,000. I hope that makes some basic sense to you. So for example, this 251 is going to represent getting 1 hit because it's between 141 and 496. I can copy and paste this down. It will change if I do the copy and paste. That's the way it's set up in the spreadsheet, so it won't be a 251 any longer in this first spot. To turn to a 702, that's okay. It's all simulation anyway. Click and drag this all down through 162 games to do that simulation. Alright, now comes the tricky part. I want to convert these numbers to a number of hits. Okay, this is a bit tricky, and maybe there's an easier way to do this, but I'm not sure offhand what it is. I'm going to use an if command multiple times. Now, what does if do? I was explaining this in lecture 16b of my class that was earlier today, and trying to do it all in a short amount of time, and it was just too fast. So now we've got a little extra time to talk about how if works. How does if work? Let's take a basic example. I could type a number in this cell like the number 4, and I could type equals if. Note the syntax. You've got 3 inputs here. There's a logical expression for the first input. There's a value if true. There's a value if false. Okay? What's an example of a logical expression? Well, for example, I could test whether the number in cell H1 is less than or equal to 5, for example. If it is, what if does is it will return an output equal to whatever you type next. So I could type a number next, like the number 7. I could type other things as well. So if the number in cell H1 is less than or equal to 5, which it is, since 4 is less than or equal to 5, you will get an output of 7. What goes next after the next comma is what would get returned as an output if the number is not less than or equal to 5. I could return a word, like the word hello, instead of a number, if the number in cell H1 is not less than or equal to 5. It is less than or equal to 5, so the output is returning a 7. However, if I make it bigger than 5, like 6, watch, the output becomes hello, that text. So that's the basic structure of how if works. Now it turns out you can nest ifs within each other in the way that I'm about to show you to do the simulation here. So for example, I could start typing if equals if the number in cell G5 is less than or equal to, what would be good to pick? How about 140? Based on the fact that if ran between is between 1 and 140, a whole number inclusive, that's going to represent 0 hits. In other words, if that number is between 1 and 140 inclusive, I do want to return 0 hits as the first thing that happens if the number is less than or equal to 140. What if the number is not less than or equal to 140? Well, the simplest thing I could do would just be to return a number like 1. However, that's not going to be quite what I want because he might get 2 or 3 or 4 hits, not 0 or 1 hit. So this is not quite good enough. This is only going to return a 0 or a 1. And it's only going to return a 0 if it's less than 140. I could keep going here until it is. There we go. 52 is less than 140, so it returns a 0. So I need to do something more complicated. The structure again is if a certain thing is true. I guess we're seeing the structure over here now. If G5 is less than or equal to 140, we're going to return a 0 representing 0 hits and 4 at-bats. You think of what comes after the comma as being else. What to do if that's not true. And I'm going to put another if expression inside here. And maybe we want to end the parentheses here to emphasize that this new if expression is what gets evaluated if the initial condition, G is less than or equal to 140, is not true. Alright, so what could be true otherwise? Well, G5 could be less than or equal to, well, let's click out of this. It could be less than or equal to 496, based on the 0.496 right here. Now, if we're in this case, we're already in the case where G5 is not less than or equal to 140. It's bigger than 140. So by doing G5 is less than or equal to 496 right here, we are already in the case where G5 is greater than 140. Might be bigger than 496 as well, but if it is also less than or equal to 496, then we want to return 1 hit. Otherwise, else, we want to apply if again. Now do G5 is less than or equal to 834, because that's going to represent getting 2 hits. If we have reached this stage with our value of G5, we already know G5 is, the number in there is bigger than 140. We already know it's bigger than 496. Is it less than or equal to 834? If it is, return a 2 for 2 hits and 4 at-bats. Else, do one more if. This will be our last one. If we're to this point, we're already to the point where G5 is bigger than 834. So now we're testing, is it less than or equal to 977? This number in D8 times 1,000. If it is, that represents getting 3 hits and 4 at-bats. Else, if it's not, now we don't need another if. Now we can return a 4 for 4 hits and 4 at-bats. Alright, did it work? It worked with this first one. 940 is in the category of getting 3 hits, and it returned a 3. Copy and paste this down. Is it working for other ones? Now it turned to 274, which does represent getting 1 hit, because 274 is between 141 and 496 inclusive. 914 is between 835 and 977 inclusive, and that represents getting 3 hits. 511 is between 497 and 834 inclusive, so that represents getting 2 hits. This is working. So now we go ahead and copy and paste it, click and drag it down. We have simulated his season. If we assume he gets 4 at-bats in each game, this is the number of hits per game. Sometimes he gets 0 hits, sometimes 1, sometimes 2, sometimes 3, sometimes 4 hits. But now we want to summarize this information. We're not done yet. We have done a simulation to an extent, but I want to do some more and I want to add some graphs. We want to count the number of games where he got 0 hits, 1 hits, 2 hits, 3 hits, and 4 hits, convert it to a proportion, and then compare those proportions with the original probability density function here, the distribution right there. All right, they won't be exactly the same, but hopefully they will be close. We can count the number of games he got each number of hits with equals count if. This is a little simpler actually. We've done the hardest part so far. We're going to look at the numbers in column H, cells H5 through H what? 166. We're going to count those as part of our count if for 0 hits if they are equal to 0. So in quotes I'm going to put equals 0 as my condition. That's the way the syntax is going to work here. So this is going to look at all the numbers that are all 0s, 1s, 2s, 3s, and 4s in column H here, H5 through H166, and we'll count them if they are 0s. And you can see the answer here is already 19 for this particular one, although if I enter this, these numbers are going to change, and it will probably change and not be 19 anymore. Yep, 22 now for this new list. Do the same kind of thing for 1 hit, 2 hits, 3 hits, 4 hits. Unfortunately, copy-paste is not going to work here. However, I remember it's H5 through H166. Now for 1 hit, I put a quote equals 1. That'll count the number of games with 1 hit. Continue, equals count if H5 through H166, comma, in quotes, equals 2 for 2 hits, equals count if H5 through H166, comma, in quotes, equals 3 for 3 hits out of 4 at-bats, and finally equals count if H5 through H166, comma, in quotes, equals 4 for 4 hits and 4 at-bats. Is that 162 games? I could use equals sum to add these up. 162 games. Confirms that. Then for the proportion, we can take each number and divide by 162. Can round these to just 3 decimal places. It's changing them every time. That's okay. Not a big deal. And then we can see how well these numbers, the proportion of games, matches the probability distribution. Try to get that in your memory, 0.14, 0.356, 0.338, 0.143, and 0.023. Yeah, not too bad. This one's a little higher than expected. This one's a little higher than expected. Yeah, okay, and let's see, these two are lower than expected. This one's pretty close. Okay, so not too bad. Then final thing to do here is to make a graph. 2 graphs comparing these things. We're wanting to make a probability distribution. It's not really a histogram in the usual sense of the word. You could just call it a bar chart. So I could highlight these 2 columns and insert chart. Let's see, I don't want that. How about this one? Bar chart. Yeah, that would be good. I'm not going to bother with the labeling for the sake of time. But basically, this is a probability distribution for a random variable. It's binomial. N is 4, P is 0.388. The heights of these bars are the probabilities of getting 0, 1, 2, 3, and 4 successes. Again, my students, you should label these before you turn it in. And then we can make a bar graph based on the K values over here, and also these proportions over here. Insert chart. That's not what we want. Let's see. I'm not sure. Maybe I could do that. No. Okay. Maybe let me just try highlighting these and hope it does it. Sometimes this acts funny. I'm not sure why. It picks things in a certain way. There we go. That looks like what I want. Okay, and the thing is, you could compare these. And my students, you should make sure you label your graphs. And they should match fairly closely, not perfectly, as far as comparing those heights. And by the way, yeah, if you redid the simulation, if I did a copy-paste here, for example, the second graph is going to change, but the first graph should not, because everything gets updated for the second one. Here we go, ready, 1, 2, 3, go. Yep, that changed. Okay, and so everybody should get a different answer. And so I hope you got a lot out of that. Again, nothing super duper fancy, but if you're interested in doing simulations with spreadsheets, this will get you going and thinking about binomial random variables at least.